Thanks, Sebastian, for the kind introduction. And so thanks for the organizers for the invitation. And in the following 1 hour, I will continue to talk about ab initio thermodynamics, but mainly focus on our recently developed method, the Replica-Exchange Grand-Canonical. Before talking about the theory or methodology, I just first we should be clear what kind of issue we want to be addressed here. And in macroscopic region, and for instance, iron is easily corroded in the humid air, becomes the rust we can see every day, and it happening every day. And what we are interested and what we want to study is that how the atom rearrange and the concentration of the materials changes when the materials is in contact with the reactive gas. So we are interested in the atomic level so that we know what happens in the atomic level to help to improve the microscopic level. And there's the method to be introduced is, I think the Professor Hoyt already have a wonderful talk about the ab initio atomic thermodynamics. I also prepared several slides because before I saw the title for the Professor Hoyt is catalytic scaling and biotic scaling. So I thought that I also need to do some tutorial talk about this ab initio atomic thermodynamics. Now I think I can just briefly introduce and go on to the main part, the Replica-Exchange Grand-Canonical Method. And if time permits, I will also introduce, say a few words about this, computational hydrogen electrode, which is an extension of ab initio atomic thermodynamics in the field of electrochemical field and where the electric potential is involved. Okay, thermodynamics is concerned the large scale observations, and the central concepts in thermodynamics is the thermodynamic systems, in our case, the surface, and its surroundings, and in our case, the surface is surrounded by the reactive gas, it interacts with the reactive gas, and the thermodynamic equilibrium. The equilibrium in the thermodynamics is characterized by the thermodynamic potentials. For instance, here, the internal energy, the enthalpy, Helmholtz free energy, this one is equals to the internal energy minus temperature times the entropy. And at the constant temperature, the Helmholtz free energy is minimized when the system reaches the equilibrium. The Gibbs free energy is equal to the internal energy plus the PV turn minus the temperature times the entropy. And again, if the system reaches the equilibrium, the Gibbs free energy is minimized at constant temperature and constant pressure. With these tools, thermodynamics, when I say thermodynamics now is classical thermodynamics, can be used to describe the systems, how systems respond when there's a change in its environment. But now the classical thermodynamics can only describe the macro effects, but it ignores the individual molecular processes. The bridge between the microscopic level and the macroscopic level is made when the Lud-Boltzmann first proposed a statistical explanation of the second law of thermodynamics and provided a current entropy definition equals to Kb times logarithm omega. Kb here is a Boltzmann constant. Omega is the number of microstates, or you can simply regard it as configurations in a given microstate. And this is only a postulate, but it works. According to the second law of thermodynamics, when the system reaches the equilibrium, the entropy is maximized. So here is omega is maximized. Moreover, the omega omega has a characteristic is multiplicated. That means the characteristic nature of the additive nature of the entropy. So with this postulate, we can get this equations that the free energy is equal to minus kBT times logarithm z, or equal to minus beta logarithm z. This deviation you can easily find in the textbook and the wiki page. And the beta here is the inverse temperature, and the z here is well known as a partition function. And in classical statistics, the partition function is the integral of all the configurations times its Boltzmann weight. So capital R here is the configuration or microstate in the potential energy surface, and lambda is the thermal wavelength. Furthermore, another way to calculate the free energy is use its probability. And the probability to find a system in an energy interval E and E plus dE is equal to the density, the probability density times dE, and the probability density can be reformulated by the partition function at the omega. And in the end, we can find that the probability is related to its free energy. So we get this equation that the ratio between the probability to find a system with energy E1 and the probability of the system with energy E2 is a Boltzmann factor of its relative free energy. So please have in mind these two equations, and this one is mainly for ab initio atomic thermodynamics. This one is mainly used in the Replica-Exchange Grand-Canonical Method. I will discuss more about these two equations later. I will skip the discussions about the ideal gas because I think Professor Hoyt already gave us very tutorial and detailed explanation how it works. I will just start this because for these equations, I just emphasize 2 points. First is we use this equation to connect, there's a relationship between the temperature, pressure, and the chemical potential. So this is how we change our chemical potential temperature into pressure and temperature. Another point is that once you understand how we treat the ideal gas, use the ab initio atomic thermodynamics, you are halfway success to understand how the ab initio atomic thermodynamics treat the solid system. I just recap here, and considering a system in contact with oxygen gas phase, and the gas phase can be regarded as a reservoir, and the reservoir can give or take any amount of oxygen to or from the system, from the surface, without changing its temperature and pressure. So we can regard this system as an isothermal isobaric ensemble. So the appropriate thermodynamic potential to describe this system is Gibbs free energy absorption, and expressed as the Gibbs free energy of the whole surface minus the Gibbs energy of clean surface minus the number of absorbed oxygen times oxygen chemical potentials. And the Gibbs free energy is calculated, sorry, here I use partition Q, it's just default symbol, it's the same as before it's that partition function. So we know that the Gibbs free energy is can be formulated, calculated by minus kBT logarithm, the partition function plus the PV term. And so if we know the partition function, we can directly calculate the Gibbs free energy, but for this complicated systems, we don't know. And we borrow some idea from the ideal gas, and the ideal gas, the partition function is a product of the partition function of different degree of freedom, that is translational, rotational, vibrational, electronic, configurational, nuclear, etc. And the same idea applied to the solid, and the Gibbs free energy is also decomposed into several contributing terms. That is total electronic energy. In practice, you can just do a DFT calculations to get your total energy. of your system, and these two are due to the solid system, the translational and the rotational free energy are discarded, and the vibrationals, the relative vibrationals for some systems are kind of negligible, or at least treat at harmonic approximation. And in practice, usually the configurational free energy is neglected also. But as we can heard from the Professor Hoyt, and it also can treat in analytic form, and the PV term is negligible here. These two approximations, however, do not always yield an accurate phase diagram, especially when the when in the high temperature and high coverage. And want to do in order to free from this approximation. Of course, this is not the problem of the ab initio thermodynamics. This is how we practical do this kind of calculation. We neglected based on these approximations, but here we want to free from these two approximations. There's need an unbiased sampling of the configurational and compositional space. Okay. Then comes to a sampling of the surface in contact in equilibrium with the gas phase. This kind of sampling remains a challenge. If you look at this example of the 3D potential energy surface, this kind of energy surface has numerous minima, and the free energy barrier between different basins are very large. More importantly, systems with many atoms usually suffer from slow diffusion issues. And for decades, many methods has been developed to overcome the kinetic barrier. They can do little for accelerate the slow diffusion issues. Open ensemble, which described in equilibrium in Grand-Canonical ensemble, provide an effective way to generate the, to elevate the slow diffusion issues. In the Grand-Canonical ensemble, atoms get in, get out of the system, and effectively generating the possible defects. And so it's kind of circumvent the diffusion bottleneck. And another point is that if you study the reactions of heterogeneous catalysis, there's also the dissociation barrier of the molecule is usually very large, around several eV. And in practice, in our Grand-Canonical, the dissociation barrier is circumvented by allowing both molecular and the dissociated atoms to insert or remove from the system. And these are the simply the how we realize the Grand-Canonical Monte Carlo. The main part is to insert a molecular or the atom at the atom position on the surface, or randomly select the atom or molecular from the already solved on the surface to attempt to remove. And the probability density of the Grand-Canonical is well defined. So it's in these equations, so the probability to try to reinsert or remove the particle is a priori known factor. And in the code, when you try to insert a molecular, you want to calculate how big the probability to get this insertion. You simply need to calculate the DFT energy of the system plus one extra this insert atom and the original system energy. As mentioned before, there are many methods developed to overcome the kinetic barrier. According to their work philosophy, they can fall into two categories. The first one category is adding the bias term to the Hamiltonian of the original system, such as method dynamics, umbrella sampling, accelerate molecular dynamics. These methods are efficiently sampling the configurational dynamics along the reaction coordinates or along a few collective variables. And the appropriate choice of these collective variables are crucial for the accurate calculations. And the choice for this collective variable is non-trivial. Another issue is that it is also not trivial to determine when the system is converged. The second category is to build a generalized ensemble. A generalized ensemble is to overcome the minimal barrier to sampling the potential energy, enhance the sampling of the potential energy by sampling a broader potential energy. The method in this category is such as simulated temporary, multi-canonical sampling, and parallel temporary, also referred as a replica exchange. The first two methods is efficiently to overcome and sampling the phase space by introducing a random walk on the phase space. And this random walk is determined based on a non-Boltzmann probability weight factor. And again, it is not a priori known weight factor. You need a lot of tests to know its priority of this weight factor. And for the replica exchange, I will talk about later that this is for this one, the weight factor is well known for different ensembles. And so we choose the replica exchange. Traditional replica exchange simulations includes several replicas, and each replica has configurations in different in a canonical ensemble and in different temperatures as shown here. And there are 8 replicas, a bunch of replicas, and different replicas use different colors, and different color is different thermodynamic state. That here is the only temperature, different temperatures. And during the simulations, the replicas try to swap with its neighboring and allow this kind of swap that the replicas at lower temperature regions have the chance to reach the high temperature regions so that it can overcome the kinetic barrier easily. And also for the high temperature replicas, because it is easily to overcome the kinetic barrier, it may not sampling thoroughly in its local minimum. So if it has a chance to go to the low temperatures, it also to improve the sampling for this inside local minimums, because local minimums is not one configuration, there's still a lot. And the partition function of this extended, you see, I always say partition function, we calculate the partition function, then we know anything. We know the partition formula, then we know the probability of etc. The partition function of this extended ensemble is a product of the individual canonical ensemble. And the canonical ensemble, the partition function is well known, so just a product of the different canonical ensemble. And this is a probability to do the swap, whether this swap is accepted or not. And we can see the probability is related to the energy difference between the two configurations. This tells us that it's better to just swap between its neighbors, and it's better when you choose neighbors, the energy distribution between the neighbors has significant overlap. Otherwise, the probability is quite low and it's always rejected. And if we have a good overlap between the neighboring neighbors, and the statistical would be better. Okay, now we combine the replica exchange and the Grand-Canonical ensemble with these two methods, and indeed we prepare a batch of replicas, and again each replica has a configuration there, and each replica in its thermodynamic states, and here the thermodynamic state in Grand-Canonical denoted by the chemical potential and the temperature. And here the different color is scaled by different thermodynamic state. And this is the schematic of REGC simulation. The x-axis is the simulation time. The y-axis is the different replicas. And during the simulation, the replicas either allowed to change, to swap between each other, or try to exchange the particle with its own reservoir. And after each replica swap or particle exchange attempt, then the ab initio molecular dynamics will follow to further relax or diffusion the configurations. And by combining these two methods, the sampling is proved by allowing the replicas at relatively low temperatures to reach the high temperature regions where the system can overcome the kinetic barrier easily, or allow the replicas at high chemical potentials. At high chemical potentials, usually you have a lot of insertion for the system. So the system has many atoms, so it has a diffusion issues is heavily. And the replicas at high chemical potentials has a chance to reach the low chemical potentials. So there's a way to exchange the particles with the reservoir. So it's kind of elevate the diffusion problems. Moreover, with the 2D scheme of REGC is designed in our approach. Unlike 1D replica exchange, each replica only has two neighbors. But in our 2D scheme, each replica at least have 3 neighbors, or at most have 8 neighbors. This will enhance the probability of configurations across different thermodynamic states. And also, the replica exchange is performed in a collective way, which means that in any of this swap type, for example, you just swap between different temperatures, but the chemical potential is the same, or you swap between different chemical potentials, but the temperature is the same, or like this cross a left or the right, that the temperature and the chemical potential are different. And in each of these swap type, all the replicas are involved. So they try to swap in one step. Okay, then come to the weight factor. And so the partition function of this extended ensemble is the product of the partition function of the Grand-Canonical ensemble. So the probability to swap between 2 neighboring replicas is priori known. And it is related to the energy difference between the 2 replicas and the temperature, and also the chemical potential or the number of absorbed particles. This probability is also give us some information that when we prepare a replica exchange Grand-Canonical simulations, we need to think that we want to have a good statistics. That means that the probability here is good enough. It's not close to 0 and it will never exchange. So we should have some overlap between the neighboring replicas. But of course, you cannot say, okay, then I just as close as possible the replicas, the neighboring replicas. This will make your computation is really heavy, and also it doesn't really make sense here. Just to make your computation very heavy. Okay, This is a flow chart of the Replica-Exchange Grand-Canonical. Before the simulation, what you need to prepare is the configurations. Either all the replicas share one configurations, or you prepare different configurations for different replicas, and the temperature range and the chemical range you are interested in. And after these input parameters are ready, then the system, the whole replicas or the whole systems has a probability of x0 to try to exchange the replica or swap the thermodynamic state between its neighboring, or 1 minus the x0 probability to exchange the particle with its own reservoir. After each particle exchange or replica exchange, each configurations, you get a new configurations, or you or the swap is rejected or exchange is rejected, you have your original ones. And these configurations each configurations will have a ab initio molecular dynamics to further relax the systems. And this procedure is iterated until the defined quantities is reached the equilibrium or converged. Okay, for this slide, I say a few comments about the performance of REGC. The method itself is embarrassed parallel, but the inherently parallel nature of the replica exchange is challenged. When the ab initio molecular the time for the ab initio molecular dynamics for different replicas varied a lot, due to that the system size of different replicas is different. It's changing. Some have a high chemical potentials. It's insert a lot of particles. Some have low chemical potentials. It maybe just stay as a pristine surface or clusters. So the number is different. And a simple and effect solution for this kind of problem. Of course, this kind of problem, if the lowest replicas make the other replicas wait until its MD finished, then leading to loading unbalance for our cluster, for our supercluster. And a simple and effective way for this issues is to participate REGC MD simulations into several REGC MD simulations with a small number of replicas. For example, here, REGC MD simulations with 64 replicas is participate into 32 replicas, and the idling time can be reduced from 20% to the 10% of the total simulation time. Okay, then come to the construct the phase diagram. To construct the phase diagram, you need to calculate the free energy. Then came to the second formula. If you remember that I want you have in mind that the free energy of the certain phase I at the certain thermodynamic state here means chemical potential temperature is related to the probability of the system to find the sampled system in the state I. And it can further formulated as like the integral form. And here the capital R is a configuration again, and Ki is the indie factor of the phase. So when we say phase, and we know that what kind of descriptor before this phase, so we call it indicator here, and the density fractional, and the nominal normalization term in the denominator is known as a partition function, and the SMO average is also calculated in this way. And if we know the density probability function, then the non-trivial task is to evaluate the partition function at each chemical potential and temperature we are interested in. And with this partition function, we can advise to calculate the free energy or calculate the ensemble average. Here we adopt the multi-state Bennett acceptance ratio to estimate the partition function. The M bar works by redefining a reduced potential for a Grand-Canonical in this form equals to the beta, that is inverse temperature, times the total energy minus the chemical potential times the sorbed particles. And with the reduced potential function, we can have Grand-Canonical density function, and the Q is in this Boltzmann factor of the reduced potential function. And the M bar will use all the data sampled in the IGC, different thermodynamic states, different configurations to estimate the partition function here. And with this partition function, we can get the ensemble average. And one thing I think I want to make you notice that here we change integral to the sum over, and this is based on the ergodic hypothesis. That is the ensemble average equal to the time average. And I will say a word here to explain how this hypothesis is, because I think in our next tutorial, Mariana will explain in detail about this hypothesis. And with this hypothesis, we can get the ensemble average of the total energy is sum over of the each energy of the each configuration times its Boltzmann factor. And moreover, the heat capacity can be calculated by the ensemble average of the total energy or the total energy square. Two examples are provided here to illustrate how the IGC works and how to prepare IGC simulation and how to post-processing the IGC simulation and what kind of results we can get from after post-processing. The first one is the Lagrange system. The other is a silicon surface at ab initio level. The frozen FCC 111 surface in contact with the B particle, B gas phase, and the B particles is only allowed to insert in this defined surface starting from the top of the surface. And the blue atom is the top layer surface particle, and the gray is the sublayer of surface, and the black is the second sublayer. Though Lagrange surface as a toy model, it is quite very simple, and one can even guess some qualitatively before you doing the simulation. It is not easy to predict quantitatively the detailed thermodynamic information, that is the structure, composition at different thermodynamic states. For comparison, we built the phase diagram, use two methods. One is, as I explained, that I use the IGC sampling data and then use M bar to evaluate the partition function to calculate the free energy. And the one with the lowest free energy is the most probable phase. This is how the left phase diagram calculated. And the second is calculated in atomistic thermodynamics way. But the lowest energy isomer is coming from the IGC sampling data. This is more than a pure atomistic thermodynamics. And by comparison, we found at relatively low temperature and low coverage, this two phase diagram is almost coincide. But there are more phase transitions reviewed in the left phase diagrams, but missing in the right phase diagram. And moreover, the phase with higher coverage compared to the right one is shift. The left one is shift to the higher temperature and lower pressure. And the particle distribution function is calculated along the Z direction. And we could clearly see that the first monolayer has the 80 B particles, and the second monolayer has 45 B particles, and even thinner second monolayer has 59 B particles. And we also have a very large coverage, around 85, as shown here. But as also you notice that the the particle distribution between the second monolayer and the third monolayer is not completely go to zero. The radial distribution function is calculated for the different absorbed, so we can get the more detailed structure information about how this phases looks like. And the radial distribution function of the first monolayer and the second monolayer has the characteristics of the solid phase, that is well-defined peaks and long-range order. And for the second monolayer phase 2, a much thinner one, that is NB equal to 59. This is the lowest energy isomer, and it has some, and the B particles occupied approximately in the bridge side and the hollow side, and forming reed-like structures along the projection of the surface atoms. And at 200 Kelvin, the reed-like structure is still noticeable, even though there's a few B particles diffusion around the surface particles. And we can also see from the average distribution function that it shares some of the major peaks with that of the lowest energy isomers. When the temperature increased to the 600 Kelvin, we see that the ring structure is not noticeable at all. And the more and more B particles are diffusion around the surface atoms, and the radial distribution only have a few peaks share the similarity with that of the isomers, and it became much more smeared. And it is also we can also say that with the increase of temperature, the phase became more and more disordered. With this, I will give a short summary for these applications. The Lagrange surfaces serve as a proof of concept to demonstrate the power of the IEGC method to provide or to predict the detailed information of the surface in contact with gas phase. Moreover, we also discussed at which conditions the ab initio atomistic thermodynamics is still a good approximation. Now move on to our ab initio applications, that is the silicon 100 surface in contact with the deuterium reactive atmosphere. This silicon 100 surface is well studied for many decades. The commonly accepted reconstruction pattern is a symmetric 2x1, symmetric 2x1, asymmetric 2x1, P 2x2, and C 4x2. And the absorption pattern 2x1 is found thermodynamic stable at around 600 Kelvin, and another 3x1 absorption pattern is thermodynamically found at 400 Kelvin, as reported by experiment. And in order to include different reconstructions and absorption patterns, 4x4 and 3x3 supercell are built. And these are the settings for the FHI-aims to perform the ab initio molecular dynamics. I think this settings is already familiar to you, but this is maybe not. If you are not familiar with this molecular dynamics, this is the thermostat I used for perform a canonical ensemble. And I will also not introduce in detail about the technical or theory behind this thermostat, because in our next tutorial, it's fully about molecular dynamics. And notice we use deuterium instead of hydrogen, because deuterium is slightly heavier than hydrogen, so the thermodynamic is more stable. The time step, we can use a slightly larger. Again, this is related to molecular dynamics. And but I want to say that experimental measurement already tells us that the silicon in contact with hydrogen and the deuterium, the isotopic effect doesn't change the absorption pattern. Okay, in the next few slides, I will explain how we quantitatively calculate the ab initio phase boundaries using the MBAR sampled data and post-processing, IGC sampled data and post-processing by MBAR. And the heat capacity is calculated is in this form. We already get it before, and the energy ensemble or energy squared ensemble at each temperature and each chemical potentials is can calculate in the MBAR. And this blue regions is the TP regions. The IGC sampling is sampled. This is a region with a sampled. The white one is out the beyond of the IGC sampling. This is determined by the temperature range and the chemical range we selected. And we estimate the heat capacity at every 1 Kelvin and every 0.01 EV interval. Then we get the TP map of the heat capacity. Here, the color bar is the value of the heat capacity ranging from 0 and 20. And besides the black, others with color is blue or purples are the means that here is a considerable CP heat capacity values, but still it is not. We cannot decide where the phase boundary is, because the phase boundary corresponding the phase transitions is usually there's a heat capacity peak, for instance. And we do another post-processing and calculate the free energy and the phase indicator. We choose the number of chemical sorbed deuterium. In the simulation itself, we allow to the molecular and the atom. So there's a molecular physics of the molecular also in the system, but in reality, we only may be interested in the number of chemical sorbed. So the number of chemical sorbed as an phase indicator here. And this is a TP map of the number of sorbed deuterium. And we different color is the different number of sorbed deuterium. And with this, we try to get the phase boundary. And the blue curve is a heat map as a function, heat capacity as a function of the deuterium pressure at 300 Kelvin. And the red curve is the chemisorbed deuterium as a function of the pressure at 300 Kelvin. At each peak corresponding a phase diagram, phase transitions, and the temperature and the pressure where the peak located is marked as a white dot here. And I will only explain the first two, others follow the similar analysis. For the first peak, the corresponding phase transition is from the pristine phase to the ND equal to 2 phase. And for the second peak, it's the 2 adsorbed deuterium phase to 8 adsorbed deuterium phase. And with the temperature increase, we can see the first peak, all the heat capacity peak is shift to the higher pressure as expected. And the first peak not noticeable before, but it's still there. But the second peak split into 2 peaks, and we could together with the red curve, we found that this peak now corresponding to the phase transition from 2 to 6, and this is corresponding from 6 to 8. So at these TP conditions, there are 3 phases coexist. So this is a triple point. We marked as a black dot. With further increase the temperature to 382 Kelvin, the first peak is totally disappear. So this is a critical point. And following the similar analysis and connecting the white dots belong to the same phase transitions, you can get the white lines here or the TP map. They are the calculated ab initio phase boundaries and also marked with different Roman numbers, and different Roman numbers is different phase transitions correspondingly. And now we have the phase boundaries, and the regions separated by the phase boundaries is the single phase stability regions. And we want to get more information about the structure information about each stability regions. And besides the number of chemical criteria, we also define two different structure descriptors. One is coordination histogram, the other dimer type. The coordination histogram is defined, for instance, for these structures, is only for the top silicon atoms. There are 6 silicon atoms marked as a purple atom, a purple ball here, and each is coordinated with the other 3 silicons and 1 hydrogen. And there are 3 silicon atoms, the gray ball, and each coordinated with 2 other silicons and 2 hydrogen. So the coordination histogram is 036, 00063. And the dimer type is defined that if the dimer is formed in on the same side, the dimer type is 0, and otherwise it's equal to 1. If we change the indicator from the number of chemical deuteria to the coordination histogram, then calculate free energy and found the lowest free energy, the lowest free energy corresponding to the most probable coordination histogram. Then we can get the TP map of the coordination histogram. Different color is corresponding to the different coordination histogram, and each histogram is in its region is the most probable ones. And the different hatching type is corresponding to the different dimer type. And we could find that at least for the, maybe we see clearly here, and for the pristine surface or the this highest coverage surface phase, there's two order disorder phases. That is at relatively low temperatures, the dimer type is equal to 0. That means that the dimer is formed in the same side. Then it will equal to 1, means that the dimer, silicon-silicon dimer bonds are dynamically forming and breaking all the top silicon layers. Okay, similar analysis can be performed for the 3x3 surface and also the structural informations. But to compare with the experimental doesn't measure, okay, this is 4x4 result, this is 3x3. No, they measure large scale. And to make this 2 data, the RGC data from 4x4 and the 3x3, 2 different supercells, we define a reduced potential function for the Grand-Canonical by further refers to the potential energy of the unconstructed surface and divided by the surface area respectively. This makes these 2 data sets comparable, and we combine these 2 data sets as a joint data and calculate to build a joint phase diagram. This phase diagram looks more like the 4x4 ones, except this highest coverage with around 1.33 marked with the orange frame here. And the 2 order disorder phase for the pristine surface and the coverage with the 1.0 is still exists. And we further calculate the average silicon bond lifetime at 800 Kelvin for these 2 phases, pristine and the coverage of 1.1. And we found the average silicon bond lifetime is for the coverage is adsorbed phase is longer than the pristine surface. This means that adsorbed deuterium slow down the dynamics of silicon-silicon bonds and makes the silicon-silicon dimer bonds more stable. Then we come to compare the relatively phase stability of different coverage. We confine our discussions in this dashed red line because this dashed red line is contain this 1.33 coverage and the 1 coverage. This two is what experimental reported. And according to the REGC results, we found that at the temperature lower than 359 Kelvin, the higher coverage is more stable, thermodynamically more stable. And after the temperature higher than 359, the coverage with became more and more stable. This is consistent with experimental observations that a 3x1 absorption pattern is found stable around 308 Kelvin, and after a mild anneal to 600 Kelvin, it becomes this 2x1 absorption pattern. And for comparison, we also calculate the free energy of these two phases, use ab initio atomic thermodynamics, and the vibrational contribution is modeled at harmonic approximation. The result of FHI-AT tells us that these two phases is coexist from the temperature of 200 Kelvin to the 300 Kelvin to the 600 Kelvin. So the discrepancy between the result of the REGC and the FHI-AT is ascribed to the unharmonic attribution. That in this case, in terms of dynamic restructuring of the silicon-silicon dimer bonds. And this kind of surface restructuring is certainly missed in the ab initio atomic thermodynamics. Okay, I don't know how many time I left.
You have 5 minutes left.
Okay, I just briefly say some more words about the thermodynamic over potential, the computational.
Oh, no, sorry, 10 minutes.
Okay, then we still have time, leave some time for discussion. And this is computational hydrogen electrode. And if you already familiar with the ab initio atomic thermodynamics, and in the electrochemical field, we are not anymore involved in the hydrogen gas, but we are involved in the proton and the electron and the potential, electric potential. And for this CHE model, the assumes that the chemical potential of these two is still of half of the chemical potential of the gas hydrogen, and the two corrections. One is a bias effect of electron in the presence of the electron, that is the EU term. The other is a pH effect, calculated by the proton concentration and further reformulated in this form. And combine this, the Gibbs free energy of your system is the first three are again the same for the ab initio thermodynamics, and with these two corrections, one is potential, the other pH. And this is just an example for the oxygen reduction reactions, and in the acid environment, it will follow the association mechanism. If you don't know what is association mechanism, it doesn't matter. It's like just involved in this 4 elementary steps, and how to calculate the Gibbs free energy of each elementary step is calculated. You can calculate it, use this delta G, for example, here, the delta G of this one and minus, the delta G of this one and minus this one, also use the correction of the proton and electron. And you can get here the delta G1, G2, G3 is the reaction free energy for each elementary steps. And for the oxygen reduction reactions, the G is a minimum of the reaction free energy, and the thermodynamic overpotential is you have the minimum, then you minus the equilibrium potential, that is for oxygen reduction is 1.23. That's how its thermodynamic overpotential is calculated in this. Okay, with this, get to my summary. And for the ab initio atomic thermodynamic method, if it is a good approximation, as we discussed, at relatively low temperature and low coverage. If your system is well defined, then a screen structures, I mean, a subset of the structures is also enough for describe your system. And of course, Professor Hoyt also mentioned that you can use cluster expansion to include the vibrational entropy, configurational entropies, and the vibrational is at the harmonic approximation. Though there's many approximation here, but it is still the main method now we are using to calculate the thermodynamic stability of the surface in contact, even with the gas phase or the water for the ORR, for instance, the electrochemical reactions. And we also talk about mainly about the recent developed Replica-Exchange Grand-Canonical coupled with ab initio molecular dynamic method. And this method, of course, can address surface compositions and geometries at the operator conditions, that TP conditions, and moreover, it also can qualitatively determine ab initio phase boundaries and the TP map of other observables. If you define your indicator, you will get. Of course, this method is in the beginning. There's a lot to do and to improve or make it better. For instance, the fixed volume, it's from the Grand-Canonical. The Grand-Canonical is mu VT, so volume is fixed. And for the solution, one of the solution is, for instance, here we built the 4x4 and 3x3 so that we have different supercell. And another more difficult issue is that insertion into the directly inside the lattice, for example, the oxidation. Professor Hoyt explained the oxidation of the metal, that oxygen go inside the metal. And in technical, the Grand-Canonical to insert in the sublayer is not easy. I mean, the probability is rather low, so your sampling statistic is not good. Of course, we are now still in the thermodynamic state. This is the topic of our tutorial, and most reactions are covered by kinetics. But the kinetics is a barrier that you always need to know your initial state and final state. And what is your initial state? The final state is determined by the thermodynamics. So maybe further to combine the thermodynamic method to some kinetic method to further address the kinetics. With this, I will end. With this, of course, I will upload the slide. So this is for each method. This is 2 books. Why is, I think this is quite famous, and this is mainly conceptual theory. And I also recommend this one because if you want to do some practice stuff and you want to do how the code working, that you also go through this book. I found this is very useful. And for this two method, this ab initio atomic thermodynamic method, I recommend this two, especially this one. I mean, I just graduated the PhD last year, so for my PhD, I really think that this kind of literature helps a lot to accelerate or to help you understand what is going on. And of course, while our paper and my thesis for our method is much more details, theoretical aspect or the technical aspect explained. And for the CHE model, and this paper is recommended. With this, I would like special thanks to Matthias Scheffler and Luca Grighelli for the, I think, last 5 years. I closely work with Scheffler and Grighelli. And since this June, then I joined the cat theory in DTU and work closely with Jens Notgroff. I thanks for the knowledge transfer, and thanks again for the organizers for the invitation and all the colleagues from Nomad Lab and the cat theory. Thank you for your attention, and I'm looking for your questions.
Thank you so much, Yuanyuan, for your nice talk. And yeah, now the discussion is open for question again. Are there any questions?
Should I stop?
Sebastian, may I ask another question?
Yes.
I asked in the last talk. Beautiful work. I've really enjoyed seeing this come out, especially the 2019 paper, and I'm looking forward to the work on deuterated silicon. My question for you is, it wasn't like
this 2090 paper does not include that is silicon cluster that we will for the tutorial, and this is silicon surface. It's different application. Just
oh yeah, I said I was looking forward to the deuterated silicon surface.
Yeah.
Anyways, my question for you is, and it wasn't perfectly clear to me, when you are using M-bar to calculate the partition function, which then you go on to calculate constant volume heat capacity, as well as, relative free energies, that depends upon the definition of a collective variable that describes surfaces, correct?
Let's call it, we call it the indicator here. For each phase, you can define the indicator you are interested, for example, number of chemical bacteria, or how you characterize the surface structures. For instance, I use very simple ones, the coordination histogram for the top layer. So if you define a different indicator for your phase, then you can calculate the phase energy, free energy, use this indicator, use M-bar, then you get the result. Yeah.
Okay, so then just a quick follow-up, more open-ended question would be then, could you imagine using M-bar plus an identifier strategy for a more complicated material, for example, like a ternary perovskite, which may form, binary oxide overlayers or more complicated arrangements of atoms, or would you need a more sophisticated sampling method?
Okay, it's really not how M-bar works or not related to RGC. It's really related of the two aspects. One is your data is really have a good statistic. For example, the RGC data is really a lot and it has a good statistic, and we make it convergence so that the analysis makes sense. Another is you need to define a good structure descriptor. At least this kind of descriptor is what you want to distinguish the phase you want. Then M-bar surely with a good data, with a good descriptor, it works. Yes.
Okay, thanks so much.
Welcome.
Are there more questions? Maybe I have a question. I was wondering how far can you go in system size? So how many atoms you can treat nowadays with your method? What would you estimate? Probably it's all a matter of computation time, but in the tutorial we will discuss silicon 2 cluster. How many atoms had your silicon surface?
Okay. For the silicon surface, for example, 4x4, I have built 7 layers and it's around 150. Just the Princeton surface. And if you absorb the hydrogen, there's more and more with the increase of your chemical potentials or decrease of your temperatures. And the computation is really cost, and I think there's one slide. Of course, for this slide, I showed how the performance of the Replica-Exchange Grand-Canonical, but indeed, you can see how many cores, I mean CPUs I used for the 64 replicas. I mean, for several months to do to reach the equilibrium.
So what is the total time here for this calculation?
The total time is just the computation time.
Yeah.
Yeah.
Yeah, but in like how many hours?
Okay, as I said, it's several months.
Several months. Okay.
Yeah, to reach
Okay.
with this kind of CPUs that you can reach equilibrium. So it's kind of cost at the ab initio, at least here, but as you see the result that it really give us the result that consists, at least for this system, it consists with the experimental, and it includes the unharmonic approximation, unharmonic contribution properly. So it's like you are increase your you increase your accuracy, then you also need to heavy computation, this kind of.
And do you see some ways to improve performance, like using other techniques, like, I don't know, machine learning is quite famous these days?
Yeah. I think there's also some outlook in my thesis. Also, I think Professor Hoyter also mentioned that this kind of embedding method, that the core part is with the QMM, which means the DFT level, and the other part, for example, is use the MM, I mean force field or machine learning. It's also a good option. Or if we can train a good machine learning potential, that the full system can use this machine learning, of course, it will largely reduce the computation.
Yeah, thank you.
I will also stay in the tutorial for today and tomorrow fully, so feel free to ask any questions. I'm ready there.
Are there more questions? If not, then I would stop the recording.